Okay, we're going to continue with an example that's in the notes of a subgroup, finding the center of a subgroup, that is all elements that commute with every element in the group. We'll look at D, our matrix that's got A, B, A0 in the first row, B1 in the bottom row. A and B are integers, A is plus or minus 1. D is a group. I think, as I mentioned in the notes, I think in some detail we proved when we had a 0 here and a B here that the set was a group. This set can also be a group on the matrix multiplication. So what is the center of Z? And I claim that the center of Z is just the identity matrix, that's it. So the identity is certainly in the center. In any group, the identity will commute, and certainly the identity matrix commutes with all matrices in D, and commutes with all 2x2 matrices. Suppose we have some matrix that's in the center. So think of this as being an element of the center. U and V, U is plus or minus 1, V is an integer, and it's got to commute with everything. In particular, it's got D, so it must commute with this. So if we have some element in the center, what would that give us? Well, when we multiply, that would give us negative U, 0, negative V, 1, and in the other case, we would get negative U, etc., and then this would give us V1. So if this matrix is in the center, then V has to equal negative V. So how many integers equal their own negative? That means the only way that can happen is V equals 0. Again, I think in the notes I provided some more detailed in general terms, but this is actually working with concrete examples of a matrix here. I might have picked different numbers and said what they could be. So far, if it's in the center, we see this has to be 0. What about negative 1? Could that be a negative 1? Well, let's see why that wouldn't be the case. And the reason that would be so we must have V equal to 0. So what else must commute? We also need what? We need that U0, and then this V, if it's in the center, then we have to have a 0 here. If that's going to commute with something, what would we have? We have that it would commute with, if we put some, maybe a 1 here, and we multiply, and also 1 here, this top row would give us U 0, 1, 1. So that would give us that. And now let me pan over in a second to what happened. But we're going to make the other calculation that U has to equal, in the other direction, that they should be equal. So we have and we'll move this over. And most of that you've already seen, so you might as well move in a little bit. And so if we have that is the case, From the other direction, if this matrix is in the center, when we multiply by that side, we would have a U, and then 0, and finally a U here, and then 1. So if this matrix here is in the center, this means that we have to have U equals 1. So to be in the center, so what we've shown by some examples that if we have a matrix in the center, then U has to equal not just plus or minus 1, it can only equal plus 1, and V would have to be 0. Anyway, so that's a concrete way of showing it. I think I used a little bit more variables introduced. Again, what I did here is I took an arbitrary matrix UV, and if it's in the center, it's got to commute with everything, so it commutes with this matrix negative 1, 0, 0, 1. And if that's going to commute, the only way that could happen forces V to equal 0. So now we know V has to equal 0. Next, we commute this matrix with 1, 0, 1, 1. And in that case, the only way that could happen is that U is equal to 1. So we've proven the result. Okay, so this concludes the notes on the subgroup, or the first set. I have other notes on a special type of subgroup called cyclic subgroup, and we'll cover those next. So I will move the camera, hopefully in the right direction. And maybe zoom back. So let's begin by looking at a special type of subgroup. So this is when we posted on Blackboard, I think I called it more subgroups. So we begin with some definitions. G is a group A an element of G. We put sort of a less than and equals less than and greater than sign around E in this parenthesis. This, by definition, is all A to the n, where n is any integer. And that's called the cyclic subgroup generated by A. Cyclic subgroup generated by A. And I'm not going to write that in the notes, I'll just put in this symbol right here, shorthand for cyclic subgroup generated by A. You can read that in the notes. So the first thing we want to do is show that I'm justified in calling it the cyclic subgroup generated by A. And that set actually is a subgroup of G. So remember, the less than or equal to, when we're applying to sets, this is a set, means one set is and this set is a group. This set is a subgroup of G. So again, just for shorthand, I'm not going to write this is a subgroup of G. That's what that notation means. So we want to show it's not empty. So how do we show something as a subgroup? So I want to use the two-element subgroup test. So first we have to show it's not empty. And if A equals A to the 1, that's certainly an element of this set. So this subgroup is not that subset is not the empty set. Again, the subset, cyclic subgroup generated by A, is A raised to all integer powers. Now remember, by definition, just the way we did where in intermediate algebra, where x to the 0 is 1, because that's the identity of the multiplication, e to the 0 is equal to e by definition. So if we're allowed to look at a to the 0, that's certainly in the set. 0 is an integer, so e is in there. I guess we didn't even have to show that, but that's another way to show it's empty. What about multiplication? Why is it closed? To show it's closed under multiplication, let x, y be an A. Then there exists two integers where x equals a to the n and y equals a to the m, and then x times y, a to the m times, or a to the n times m, would be a to the n plus n. That's an integer, so this would be an element of the cyclic subgroup generated by A. So we've shown that it's closed under multiplication. What about inverse? So if we look at A, so if we take a typical x right there, if x is some element of A, as before, there exists an n with x equals a to the n, then x times a to the negative n is the same as a to the n times a to the negative n. So x to the negative n, x times a to the negative n would equal a to the n plus negative n. That's a to the 0, which is the identity. So A inverse is just x to the negative n, and that's certainly an element of this subset, because that's how we define negative n is an integer, so it can be realized as x raised to an integer power. So we have, therefore, this is a subgroup of H, because we proved that it's not empty, closed under multiplication, and also closed under, it has inverses. We give another definition now of a cyclic group. A group G is called a cyclic group if there's some element in G where the cyclic group generated by A is the whole group. And in this case, we say A is a generator for the cyclic group G. So cyclic group, I think about it as sort of hand in hand in the definition as a generator. To have a cyclic group, that means you must have some generator. Well, let's prove a theorem now. Every cyclic group is abelian. So we're going to prove that theorem. You might have an idea how to do it. We've already sort of covered that by some of the notes. Let me just tilt this just ever so slightly. Is that good enough? That's maybe a little too slightly. All right. We'll just not right that close to the side of the board there. Okay, so let's prove this theorem. And so, proof, let G be cyclic with generator G. Then for all x and y in G, if it's cyclic, we have a couple of integers m and n in Z, just like before. For x, maybe I'll switch what I call it now is G to the m, and y is G to the n. And x times y is G to the m times G to the n. By definition of how we, the integer of the exponents, the way we work with exponents in the group, would be this. But this now here, the exponent, this is m plus n. This is ordinary addition, so this would be n plus m, which would take us to g of n times g of m, which gives us yx. And that's what's required, right? So it's abelian, right? For all x and y, x times y is y times x. Cyclic groups are abelian. So a question that we'll return to, I will write, I put in the note, is every abelian group cyclic? We shall see. You may already have some examples with that or not. So an example, let G be the complex numbers, take away 0, the non-zero complex numbers under multiplication. Recall the groups with n elements which was e to the I 2 pi n times k, where k went from 0 to n minus 1. What can we say about this set? This is actually the cyclic subgroup generated by e to the 2 pi I over n. So basically, if we take k equals 1, that is one generator of this cyclic group. And hopefully that's pretty clear, right? To take any other powers here, you would just raise it to this exponent, and you would get back that, right? E to the I 2 pi k over n is equal to e to the I 2 pi over n, all raised to the k. And so that's an integer power of this element. So it's got to be in a cyclic subgroup generated by that element. We now also agree to the definition, the order of an element in a group G. So first, the order of an element A is defined to be the number of elements in the cyclic group generated by A. So just to recall, this we call the order of a group is the number of elements in a group. And we know that with an absolute value, we do the same with an element. So the way we say that is this is the order of an element. By definition, it's the order of that cyclic subgroup generated by it. So again, we have two different concepts of the order, but they're really related, right? The order of a group is just the number of elements in the set. How do we define the order of an element? The order of the element, well, that element generates a cyclic subgroup, and we count the order of that cyclic subgroup generated by the element is defined to be the order of the element. So again, that's what this is saying. This is the order of an element. And that, the right-hand side is the order of the group. So let's look at an example then. So in particular, as elements, e to the I 2 pi over n as an element of the complex, of the group of non-zero complex number would have order n. Because a few classes ago on groups, we've shown that there were exactly n elements in this group, and this is a generator for the group, so by definition, the element of this element here, the order of that element is g, is n. So let's look at another example. Let's look at Q take away 0, the non-zero rational numbers under multiplication. Then the subgroup generated, the cyclic subgroup generated by Q, which would be 2 to the n, where n runs through all integers. That's what that would be under the group operation, multiples of 2. And what I claim is the order of this subgroup is infinite. There are infinitely many units, and so how can I do that? Well, what I claim is if n is not equal to m, then q to the m is not equal to q to the n. And so therefore, there are infinitely many different integers. Each different integer gives you a different power of 2. So I think this is pretty clear, right, just from facts about exponents and how we raise numbers. Well, let's look at a little bit of a proof to it. So what happens if m is not equal to n, we may assume, and here, as I often do in the notes, I mix up the notes with what I do in the board. When there are symmetric cases, I may prove a different one in the notes. So I think in my notes I prove that, let's assume that m is greater than n. But here, let's reverse it. Let's assume n is greater than m. Because the proof of the other case, where m is strictly greater than n, is similar, and that's actually done in the notes. Suppose 2 to the m equals 2 to the n. So if we divide both sides by 2 to the m, that leads to 2 to the m, 2 to the, sorry, that would be 1 here. Right, this is a fraction, numerator and denominator is saying it would be equal to 2 to the n minus m, where this is positive. And that's certainly a contradiction, right? How could 2 raised to a positive number be 1? So where did we get this contradiction when we assume 2 to the m equals 2 to the n? So these must not be equal. And so there are infinitely many powers of 2. So we can actually show, this is not a definition, and we haven't proved this, but something that you can think about why it's true. One can show that the order of an element A in a group G is the least positive integer, strictly greater than 0, that's what positive means, with A to the n equal the identity, and if no such integer exists, or always an integer exists, 0, A to the 0 is always the identity, but if no such positive integer exists, then the order of A is infinite. So the order of an element, sort of one definition when you have a finite order, an element of finite order n means A to the n equals the identity, and n is the smallest positive integer. If you have an element of infinite order, that really means no such positive integer exists. Okay, so next we'll look at a way to test. We've had 2 subgroup tests, right? One, you usually start with a non-empty set, so that's not kind of considered a step. One was a 2-step showing it's closed under multiplication and inverses. One was shown that if you have 2 elements in the subgroup, the subset, the product of one with the inverse of the other is an element of the subset, and that would be enough. But here's a special one for when you have a finite subset. And really the technique behind this proof is kind of how you can show that the order of an element is the least positive integer. When you raise the element to that integer, you get back the identity. So here's the theorem. Let G be a group and H a non-empty subset of G with only finitely many elements. then H is a subgroup of G if H is closed under multiplication. So you don't even have to worry about inverses to show this, or to show a finite set. So I'll prove this, and again, I'll give a sketch of the proof and work through it. The more detailed write-up by Louis is in the notes. So what do we got to do? I think we only need to show that if X is in H, then the inverse of X is in H. So that's all we need to show, right? Because we've got a non-empty subset. It's closed on the product, so by the two-step subgroup test, which I call the subgroup test Roman numeral 1, we only have to show the inverse is the only piece missing. So how will we do that? I define T to be this set, A1, A to the first, A squared, A cubed, etc. A equals 1, 2, ... Notice this is not the cyclic subgroup generated by A, because the cyclic subgroup generated by A is not just the positive integer powers of A, but all powers of A, including A to the 0, the identity, and then including A to the negative numbers, which, as we've seen, if you think of a group element raised to a negative number, that's the same as raising, say, A raised to the negative 3. That's the same as A inverse raised to the third power. So this is not quite. We only consider positive power. So certainly T is a subset of H. So T has finitely many elements. T is a subgroup of H. Why is T a subset? Sorry, subset of H. Because A is in H. Or X, I think I said. We should switch something, so let me try to follow the notes at least a little bit. Let me switch this to A. Okay. So A is in H. So if we H is a subgroup. We don't know H is a subgroup of. So, but if A is in H, A squared is also in H, right? Because it's closed under multiplication. So A times A, or A squared, is in H. Well, now A squared is in H, so A cubed is A squared times A squared and A are in H, so A cubed would also be in H, etc. All the positive powers of A are already in H because A is in H and H is closed under multiplication. So we have a subset inside H. H has only finitely many elements, so T must have only finitely many elements. So what this means is there exists an I not equal to J, I and J positive integers with A to the I equaling A to the J. I think when I first introduced this is sometimes called the pigeonhole principle, right? You've got, look at these values. There's infinitely many A1, A squared, A cubed, etc. Each integer gives you an A raised to the power. So there's infinitely many ways to write A to some integer, but only finitely many of them are different. So that means at least 2 of them have to be the same. And again, I'll mix it up here. Since I is not equal to J, in the notes, I think I did it with J greater than I. So here I'll do, we may assume that I is greater than j, or I minus j is positive. But if we take this equation, ai to the aj, and divide each side by aj, or really what we're really doing is multiplying each side by j to the negative 1, so we have ai times a to the negative j is equal to aj times a to the negative j, or here we add exponents, so that's a to the I minus j equals a to the 0, or a to the I minus j equals e. So we have this equation. Okay, well, how is this going to help us? So first of all, what we want to note is that I is greater than j, so if I minus j, it has to be positive, so I minus j has to be greater than or equal to 1. If I want to say now. So I minus j is greater than or equal to 1. So if I, so we look at two cases. The first is when it's exactly equal to 1. Case A, I minus j is equal to 1. So then this equation, a to the I minus j equals a, so a to the 1 equals the identity, and then clearly a inverse is just equal to the a to the 1 inverse, e inverse equal to e, which is the same thing as a. So a inverse is in T, so it's inside of H. Again, that's the case if I minus j has to be positive integers, so if it's exactly equal to 1, that really means a is equal to the identity, and so a to the 1 is the identity, and the inverse would also be a to the 1. And so we'd be covered in that case. We certainly have the inverse of a would be in T. What if not? So what's the second case? Case A is that number that is greater than or equal to 1 was exactly equal to 1. Case B would be I minus j is strictly greater than 1. So I minus j is greater than or equal to 2. So if we subtract 1, I minus j minus 1 is greater than or equal to 1. Then what do we have? If we look at a times a to the I minus j minus 1, that's the same as a to the 1 times a to the I minus j minus 1. So adding up the exponents, that's just equal to a to the 1 plus I minus j plus 1, or just a to the I minus j, which remember, because these sets, we had that agreement here, we were able to show that means that this is equal to a. So what does that tell us? So that tells us that, well, if I look at that, I think that tells me that a inverse is a to the I minus j minus 1. Right? Because I multiply a by a to the I minus j minus 1. That takes me back to the identity, so that allows me to, so that's exactly what it means for the inverse of a to equal that. But this is an element of T, which is itself an element of H. Why is that? That's since I minus j minus 1 is greater than or equal to 1. So if we look at our list of t's, a to the I minus j minus 1 has to be in this list of t, and t was inside of h. So in either case, we have shown that if a is an element of h, its inverse is also an element of h. So therefore, h is a subgroup. So again, the upshot of that theorem is that tells us that if a set is a if a set is a finite set, very important. If a finite non-empty set is closed under multiplication, that's enough for that set to be a subgroup. In other words, the closure under multiplication, as well as the finitely many elements, forces you to have inverse in that set as well. Inverses in that set as well. Here I put an as required to indicate that that takes care of the proof, right? Because the only thing we had to prove was that it was closed under inverses. And by looking at two cases, one case was kind of the easy case that A works out to be the identity, so certainly the inverse of that is going to be in that list. And the other case, if A is not the identity, we can show that the inverse of A has to be in that list of A to the first, A to the second, etc. So we next define another important set that turns out to be a subgroup. So we'll conclude with this definition and then showing that it's a subgroup. Let G be a group, A an element of G. We define C, and they put a little subscript G here, of A to be all the group elements X such that AX equals XA. This is called the centralizer of A and G. And often, because we usually only talk about one big group, G, so often we write C of A for C of G of A. I mean, not all the time. You might be looking at what's the centralizer of some element in the rationals versus being in the real numbers. Then we have to be clear. But usually it's clear what sort of the overlying big group G is, so we would just write C sub A for the centralizer. And now a theorem. Given a group G and an element in the group, the centralizer is a subgroup of G. Again, in the notes I tend to more often write out the phrase is a subgroup of, but when I'm giving the lecture notes that I'm recording, I just use that less than or equal to sign. When there are sets here, that means something is, and this set's a group, this means this set is a subgroup of that set, of that group. So let's prove it. Let's try to do the subgroup test. So C of A is not empty. There's a whole boatload of stuff that is in A. Certainly in C of A. Certainly A is in the centralizer of A. Since AE equals EA. And that's enough. We're already done, but let me just show another one. A is in the centralizer of A. Since A times A equals A times A. Again, what the centralizers are, you fix an element. So you give an element, the centralizer of an element are all the group elements that commute with that single fixed element. That's different than the center, right? The center of the group are all the group elements that commute with everything in the entire group. The centralizer of a particular element are just those elements that all they need to do is commute with that fixed element A. So we've got a non-empty subset. Let's show it's a subgroup. Let's show it's closed under multiplication and taking inverses. So let's prove that if we take two elements in the centralizer A, that implies that product is in the centralizer. So how do we get in the centralizer? You got to commute with A. Well, A times xy. We do the associative law. And x is in the centralizer, so it commutes with A. So that gives us xa equals y. You can probably see where this is heading. Associativity again. xay. But y is also in the centralizer, so we can flip it and get xya. And this then, associativity one last time, is xy times A. So the upshot is xy times A equals, well, doesn't matter which side I put the equation, A times xy is equal to xy times A. And that's exactly the membership criteria being the centralizer for x times y. Next, let's show x. Next, we prove x in the centralizer of A implies x inverse is in the centralizer of A. So x is in the centralizer of A means that ax is xa. So, and I won't be as careful with the distributive law or the associative law as I was in the notes, but if we hit on the left and right by the x inverse, so I'll multiply this on the left and right, and multiply xa on the left and right by x inverse. But these two bump off, so we have x inverse AE equals E xa, or no x, right? These two are E, so just A x inverse, or x inverse A equals A x inverse. And that's exactly what we want to show. That's the membership criteria to be in the centralizer. X inverse commutes with A. So we've shown it's not empty, and we've shown that it's closed under two elements in the centralizer. Their product is in the centralizer. An element in the centralizer, its inverse is in the centralizer. So by the two-step subgroup test, or what I call subgroup test, Roman numeral 1, we have that the centralizer is a subgroup of G. So we'll pick up shortly, but I'm going to have to wrap up this abbreviated lecture now.